This is a joint work with Antonio and Guy. So we are looking at probabilistic circuits. It's a kind of tractable probabilistic models. By tractable, I mean they can answer many inferences with exact answer and very efficiently in polynomial time. This is an example of the circuit. You may also know such circuit under many different other names, like SPNs, PSDDs, or CNETs. For more detail, please check out Guy's tomorrow morning tutorial. More important than the names is the properties. So if you want to answer many different classes of tractable inferences, the circuits are required to have certain structure properties. For example, smooth and decomposable circuits for marginal and conditional, deterministic and decomposable circuits for MAP. I won't go into the detail of the properties, but if you're interested, please check out our tutorial. However, if you have more complicated questions, like the KL divergence of a distribution given another, this is a typical task in statistics. Or you want to multiply two distributions, or even more, you want to take the expected predictions. This is a popular topic in machine learning. It deals with how to handle missing data if you want to train a discriminative classifier. If you want to answer such advanced queries, these properties are not enough. You need more. You need structured-decomposable. Here, our paper is about how to learn such a circuit that can answer such advanced queries. The current learning algorithm is learn PSDD. The learning routine starts from some initial structure, and then it updates the structure iteratively. For each iteration, it generates many candidates, and then score the candidates and pick the best. The step 3 is very expensive because you need to evaluate the candidates, each candidate at each step. Therefore, we propose a more simple and more scalable algorithm. We have a better initial structure. We only need to generate a single candidate for each iteration, and we can use very fast heuristics. No need to score in them. From Strudel, we can learn very fast single models, and even we can scale more to the very fast mixture models. So as an outline, I will begin by introducing some background about probabilistic circuits, and then introducing our scalable learning algorithm, and then use the circuits to answer some advanced queries, and making conclusions in the end. So as a recap, probabilistic circuits encode some drawn distributions via computational graphs. This is the same example as before. It has 3 types of nodes. The input nodes are any tractable distributions. For example, it can be an indicator function, which we use in the circuits. The product nodes are factorizations defined on the input of the products. The sum nodes are just mixture models weighted by the parameters. Then I will introduce our algorithm. So our goal is to learn a structured-decomposable circuits. And what it means to be structured-decomposable? It means for every product node, if they are defined on the same set of variables, they need to decompose in the same way. And this way is encoded by a V-tree. For example, in the picture, the circuit in the left is decomposed according to the V-tree in the right. We can look at the green node here. It has 2 subcircuits, the leaf node X3 and another subcircuit defined on X1 and X2. For the green node at the bottom, it also decomposes on X3 versus X1 and X2. This is mapped to the green node in the V-tree. It has 2 branches over X3 versus X1 and X2. So this means to be structure-decomposable. And we know what it means to be structure-decomposable, and then how to enforce it in the circuits. The base case is the initial circuits. We want to start from very simple but kind of expressive distribution, and then compile it into circuits and a V-tree. Then what distribution shall we use? We use a classical child tree algorithm as our best initial circuit, because we can easily compile it into structure-decomposable circuits in linear size and in linear time. Child tree is also the best tree model we can learn according to the KL divergence given the data. After the initialization, how to improve the current structures? We want to have a more complicated structure so they can encode more expressive distribution. But at the same time, we also want to keep in all the good properties. In our case, we still want the structural decomposability. We can perform a simple split operation. By a split operation, it first pick an age, as colored red here, and then pick a variable b. Then it makes two subcircuits, their condition on b being false and b being true respectively, and then link the subcircuits to the pick an age. From this, we can see by performing a split operation, we are introducing a new subcircuit. Thus, the circuit is more complicated, and we are introducing new parameters. Thus, it can be more expressive. So about the split operation, how should we pick an age and a variable to split on? So to pick an age to split, in decision tree learning algorithm, we all know that we don't want the number of nodes to be larger than the number of samples. So here we are taking a similar heuristic. We pick the age with the most samples flowing through. Therefore, by split on the age, we can introduce more parameters to best fit the samples there. Then how to pick a variable to condition on? After the split, the variable will appear at the top of the subcircuit, and all the other variables in the scope will be conditioned on the picking variable. Therefore, we want to take the variable with the strongest dependencies among the others. Here, the dependency is estimated by the mutual information in our algorithm. So from the split and from the initial structure and from the split, we can learn very good single models. Here is a table from some benchmarks. We can show that we have good improvement compared with previous learner, especially on the larger data set. So right now we have very good single models, but can we fit the data better and scale more and have even better performance? A natural and a practical task is in probabilistic circuits is to learn mixture models. We can scale more with the mixtures. However, learning the mixtures itself is not very easy. We have two difficulties. First, we want the mixtures to be structurally decomposable as well. Therefore, we can use the mixtures to answer the advanced queries we mentioned before, which means each component have to be structurally decomposable, and they all have to conform to the same weight tree. This is not easy. Also, the scalability is another problem. If the mixtures have many samples, it's very memory inefficient, and also evaluation and learning is very expensive. To solve these two problems, our solution is very simple and interesting. We learn the mixtures and they share the same structure, but they can have different parameters. By sharing the same structure, they naturally conform to the same weight tree. Thus, we solve the problem 1. And also, it naturally solves the problem 2. Because learning is simple, we only need to learn the parameters in the mixtures. We can use any structures, or we can use our previous learned structures. And also, they're memory efficient. We only need to catch one circuit structure in the memory. More importantly, they are very computational efficiency by circuit flows. As a function shown here, to calculate the log likelihood, you only need to multiply this bit vector with this matrix. This matrix is all the parameters in the circuit. For the detail of the circuit flows, if you're interested, you can check out my poster session. I cannot go into the detail here. So now we have very good circuits which are also structurally decomposable, and we can use them to answer advanced queries. Here, for example, we compute the expected predictions. From the plots, we can see the single models already perform better than the baselines, and also the mixture models can help reduce the error even further. So some takeaways from this presentation. Probabilistic circuits can answer some advanced queries if they are structurally decomposable, and we propose a very simple and scalable structured learning algorithm. The scalability is achieved by our very fast heuristic, by our very cheap mixtures, and they share the same structure, and by the use of circuit flows. For the circuit flows, this is a quick tailor for the poster session in the afternoon.
Okay, thank you, Meihua.
That's all for the presentation.
Sorry.